Hi everyone, this is Dr. Anjani, Assistant Professor of Physics, RMD Engineering College, Kavaraipete. Today we are going to see Unit 4 topic Density of Energy States in a Quantum Well Structure. In the diagram, we can see the quantum well. The other name for quantum well is two-dimensional structure. What are quantum confined structures? The first picture shows a bulk material which is a three-dimensional structure X, Y and Z. The second one shows a two-dimensional structure and the third one is one-dimensional quantum confined structure and this is the zero-dimensional structure. The other names for 2D is quantum well, 1D is quantum wire and 0D is quantum dot. So these three are called as quantum confined structures. The restriction of the electrons to move in one or more directions by the potential barrier, then those structures are called as quantum confined structures. In this topic, we are going to find how many number of available energy states are there within the energy interval dE. The quantum well can be defined as an electrically isolated region like a thin film where the motion of the electrons are restricted in one dimension and they exhibit quantum behavior. Here the electrons are free to move in two dimensions. That is why these quantum confined structures are called as two-dimensional structures. In the diagram, we can see the two-dimensional structure, the circular disc or plate-like structure. Here, there are number of concentric circles can be drawn. Two such is shown here. One is considered as circle 1 and another one is considered as circle 2 as shown here. From the origin, the first circle has the radius n and the second circle has radius n plus dn. And the energy of the first circle is E and that of the second circle is E plus dE. So density of states can be defined as the number of available energy states per unit area in the energy interval dE and the radii dn within the small radii dn. In the two-dimensional structure, quantum confined structure, the quantum numbers considered are nx, ny for the two dimensions. Here, for the first circle of radius n and energy E, the area is pi n square. And then for the second circle with radius n plus dn and energy E plus dE is pi n plus dn the whole square. Here the positive quantum numbers have to be considered. Therefore, in this two dimension, only one quadrant will have the positive value, that is x minus x, y minus y. In this, these are all coming under negative quadrants and only one will have the positive integer value. Therefore, the Number of available energy states with a circle of radius n is taken as pi n square, and it is multiplied with 1 by 4 for the positive integer values. Similarly, for the second circle also, it is multiplied with 1 by 4. Now we are going to find within the energy interval d and between the circles of radii n and n plus dn, that is the radii difference is dn, we are going to find how many number of available energy states are there. Therefore, we are going to subtract a n from a n plus dn. Thereby, we get pi by 4 n plus dn the whole square minus n square. We get n square plus 2n dn plus dn square, just like a plus b the whole square, and then minus n square. Plus n square minus n square get cancelled off, and then the dn, the radii difference is very small, therefore the dn square will be very small, so it is of negligible value. That is why dn square is neglected. Thereby we get pi by 4 into 2n dn, and after cancellation we get pi by 2 into n dn. Therefore we get pi by 2 n dn. Let this be equation number 1. Now the energy of the electron is n square h square by 8m L square. Or since we have n form here, this n square is taken and the remaining is consolidated on the other side. N square is equal to E into 8m L square by h square. Then differentiating n with respect to E, we get 2n dn. 8m L square h square, all these are constants. Only E will be differentiated. Therefore, we get 8m L square by h square, and then E is dE. Then this 2 is taken over the other side. We get n dn is equal to 1 by 2 into 8m L square by h square into dE. So this is taken as equation number 2. So equation 2 is substituted in equation 1 in pi by 2 n dn. So we get pi by 2, this is for n dn. So we get pi by 4 8m by h square L square into dE. So density of energy states definition is the number of available energy states per unit area. Therefore, the area of the circle here is taken as unity. Therefore, L square get cancelled off. We get pi by 4 8m by h square into d. According to Pauli's principle, each energy level provides 2 electron states. Therefore, multiplying the equation with 2, we get pi by 2 8m by h square into d. Now, density of states for the two-dimensional structure can be obtained by h square should be replaced by 4 pi square h cross square, because h cross is called as reduced Planck's constant, that is h is divided by 2 pi, then H is equal to 2 pi H cross. Therefore, H square is equal to 4 pi square H square. Substituting H square as 4 pi square H cross square, we get pi by 2 8 m by 4 pi square H cross square into d. Here pi power 1 and here pi power 1 get cancelled off. 2 into 4 8, 8 get cancelled off. So we get m divided by pi H cross square into dE as the density of states. That is, for a two-dimensional structure, m by pi H cross square, the difference in energy dE. The dE is written as E minus En, and the summation, let there be n number of energy level. Sigma denotes the movement of the particle electron in the two-dimensional structure. It is a step function as shown in the diagram. So these are the quantum well structures, and the graph is shown here. Thank you.